So, hello student to the foundation of classical electrodynamics course. So, we are still in module 1 studying the mathematical preliminaries. So, today we have lecture number 5 and we will going to cover the spherical coordinate system that we started in the last class, and then like to understand what is line, surface and volume element in a given coordinate system. Today we have class number 5. So, we already started the concept of spherical coordinates. So, let me do it once again. So, in spherical coordinate, we define a coordinate system here . A point here R, this is the point. This coordinate is say r, theta and phi in spherical coordinates, but this point can also be written in terms of Cartesian coordinate, and I should write it x, y, z. Now, what is theta, what is phi here? If I join this, so this value is r, this angle is theta and this angle is phi. These are the three coordinates that basically define a particular point P on this system. Suppose this is my x coordinate, y coordinate, z coordinate in Cartesian coordinate system, but I can also define a point in terms of r, theta, phi, which is the spherical coordinate system. So, if I now try to understand what is the relationship between x, y, z and p, r, theta, q, then I can write it here. So, x is simply equal to rho cos phi, because this projection, whatever the projection r is making, let us, so from here to here this is rho, suppose, then we convert this rho to r, then we have y, which is simply rho sin phi, and okay, I should write it in different color, but anyway, and z is equal to r, because r is already there. So, z component should be r of cos theta. Now, what is rho? Rho equal to, because this is rho, if this angle is theta, then I can simply write rho is nothing but r of sin theta. Now, x, y, z I can write in terms of, so this is my x, y and z in terms of r, theta, phi, it simply gives us r sin theta cos phi, r sin theta sin phi, just replacing rho, and r cos theta. These are the relationship between x, y, z and r, theta, phi. We can also have the other way, that means let me write it. What is r here, what is phi here, and what is theta here in terms of x, y, z, that we can also write. And what is r? R is simply x square plus y square plus z square whole to the power half. Phi, you can see from here, it is simply tan inverse of y by x, like we had in the cylindrical system. Theta, because this is theta, this angle is theta here. So, theta is cos inverse, then z by r, which is cos inverse, and then we have z divided by the value of the r that we already get here, root over of x square plus y square plus z square. So, this is the transformation from x, y, z to r theta phi in spherical coordinate system. Well, now let us do what we did last time for other coordinate system, and that is transformation of unit vector. Well, that we do for say Cartesian coordinate, we have I, j and k unit vectors, and I want to understand that how these things are transformed in spherical coordinate system with the unit vector r theta phi. Okay. So, let us draw the picture that will be useful. So, these are the coordinate system. Okay, this is my x, this is my say y, and this is z, and let us draw a line here. And a point here. And then this length from here to here is my r. This is my r. This angle here is theta, and this angle is my phi. So, these are the three coordinates. So, this is r, this is theta, and this is phi. Now, in terms of unit vectors, if I try to understand what should be the unit vector associated with these coordinates. So, the unit vector r will be along this direction. So, this is r unit vector, which is making an angle here. This angle should be theta by geometry. Okay. What is the unit vector of this theta? That will be, if I draw a curve here, tangentially it should be downward. So, it is like this. Say this is my theta unit vector. So, I am having an angle here. So, let us name this angle say this is alpha. And what is the phi unit vector? Phi unit vector should be again tangentially. If I am having a surface here, curved surface, tangentially it should be along this direction. So, that is my phi unit vector. Please note that r unit vector, theta unit vector, phi unit vector, they are forming an orthogonal system here. So, these angles, whatever the angle they are making here at this point are 90 degree. But we need to find out what is the component. If I now decompose this r unit vector, theta unit vector and phi unit vector along x, y, z, then I should have a relationship with I, j, k and r theta phi. That is my goal here. Okay, in order to do that, we can extend few things. So, for example, so this is the line I am having. So, parallel to x, I can have one line here. And parallel to y, I should have a line here, so that it will be easier for me to decompose everything. So, now if I just put this theta here, because theta this phi unit vector, if I just make a projection of this phi unit vector, it should stay like here. Just I am dragging this phi vector here to here in this and this angle should be phi, because whatever the angle we have, because they are parallel, these are the parallel. So, this should make an angle phi here as well. So, this is unit vector phi. It will be easier for me to decompose along the directions. So, mind it, this is the negative, this is the x direction, this is the y direction, because parallelly I am just drawing the line, and then I just replace these things here. It will be easier to decompose. That is the reason. Now, we can have another relationship with alpha, because alpha is the angle that I need to resolve. I need to use certain relationship, because it is following certain relationship, and that is alpha plus theta. It has to be pi by 2. From the geometry, it is clear. So, that alpha is pi by 2 minus theta. You can see that r and theta unit vector, they are making 90 degree. So, alpha plus theta has to be 90 degree, because this is a straight line. So, with this picture, now we can decompose one by one. So, let us do that. Okay, let us do that. So, first thing, decomposition of r vector. R unit vector, whatever the r unit vector we are having, which is hanging in the space, I need to decompose along x direction, y direction and z direction to find out its components in terms of I, j, k. That is all. That is the goal. So, if I want to find out what is the z component of r, then it is easy, because you can see that it is making an angle theta along this z direction. So, it should be simply r unit vector cos theta of that. Cos theta of that. Then I want to know what is the x and y component. Now, you can see that r is hanging here, but I can make a projection of r over this space, over this plane, x y plane, and if I do, I simply have the projection simply have this value. Okay, let me draw it in a different, write it in a different color. This is simply r sin theta. This is the projection of this r vector, whatever the r vector we have, on this xy plane, and then I am now having r vector here lying in the xy plane. Now, if I want to find out what is the x and y components, it will be easy. The x component will be simply cos of phi, and the y component should be sin of phi, sin theta. This is the projection and sin phi. This is the decomposition of r. Okay. Now, I want to do the same thing, decomposition of, so yeah, I will like to have the decomposition of r. Then okay, let me do this here. So, I need some space, so better make it here. So, 2. Now, I theta. So, these are the components, mind it, these are the components we are looking for. Z component, y component, x component and y component. So, components. So, which component I go here first? Say, let us first check what is theta. Theta is, you can see that theta is hanging here with an angle alpha. So, the first thing that we can do, we can decompose this theta along the z direction, but you can see it is going in the downward side. So, the component that we are getting is the minus z component. So, minus z component along the opposite direction is simply theta unit vector and making an angle alpha. So, theta unit phi unit vector, theta unit vector making an angle phi here. So, it is theta unit vector, then cos of alpha. So, I am having theta unit vector and cos of alpha. Now, we have a relationship with alpha and phi, that alpha plus alpha and theta, that is alpha and plus theta, alpha plus theta was pi by 2. So, we are going to exploit this expression, and that leads to theta unit vector, so sine of theta, that is my z component. What about the x and y component? So, the x component, again I can have the projection over this xy plane, and if I make a projection of this theta over xy plane, it should be theta of sin alpha, because cos alpha was the projection along z direction. So, xy plane, the projection will be simply theta unit vector sin alpha, and then this is phi. So, this is making an angle phi. So, it should be simply cos phi. So, eventually we will going to have that theta unit vector cos theta, because sin alpha is equal to cos theta and cos phi. In a similar way, for y, I simply have theta unit vector cos theta and sin phi. Sin phi. Okay. This is the component that we have, theta unit vector component, that I can distribute in x, y, z, because this is hanging, this vector is hanging, all these three vectors are hanging in the space. What we are doing, that we are decomposing its component along x, y, z, the Cartesian coordinate system with the geometry that we are having here. So, 2 decomposition is done, the final one. Decomposition of phi unit vector. So, I have the component first. So, let us start with z component, and then what is z component here for phi unit vector? You can see that the phi unit vector is lying here, which is parallel to the, in all cases it should be parallel to the x and y plane. So, that is why we should not have any kind of z component of this phi unit vector, because phi is tangentially over this. If we have a curve like this and it is tangentially around this direction, so we should not have any z component. So, z component of the phi unit vector is simply 0. Now, already we make a projection because it is parallel to x y plane. So, I am having a projection, it is lying in the x y plane rather. Now this angle is phi. Now, the things are very simple. So, I just now divide this along this y direction and along this x direction, and if I do, you will simply get this. So, minus x component we will first find, because it is in the opposite, because you can see that it is in this direction. So, first you have this component here, which is the minus x direction, and that component is simply phi unit vector, and then sin phi, and y component is phi unit vector, or I should write it as a, this is not, this is that component I am dividing, cos phi, that is all. So, should make a this sign, so that these are, yeah, the way I did, this is a component. So, 3 different components I divide. Now, after having the division of component, now we are in a position to write the entire thing in a matrix form, that the way we did. So, this component z is nothing but the k unit vector, x is I unit vector, and y is j unit vector. So, I can write any vector in this way, I j k in terms of r theta, and then I can make a transpose and I will get the other one. So, if I write now finally my I j k, these are the 3 vectors which I decomposed, and this decomposition, whatever I decompose, if I now write, then all the x components what we get here, I need to gather that, and then I will find. So, it should be simply sin theta cos phi, then cos theta cos phi, because I am just putting the components which the component I decomposed, x component sin theta cos phi, then what, x component sin cos theta cos phi, and then x component minus of sin alpha, minus of sin phi. So, here I should have minus of sin phi. What about the y component? Similarly, sin theta sin phi, then cos theta sin phi, and then cos phi. These are the y component, and z component, all the 3 cases, cos theta, then minus of sin theta, and 0. For final case I am 0. This side I should write r unit vector, then theta unit vector, and then phi unit vector. In the books you will only get this matrix form, but how it came normally it is not given. That is why I thought that I should do all these things explicitly, so that you can have an idea that how from one coordinate system how the unit vectors are changing, transforming in another coordinate system. So, here you just check by yourself that how these components are decomposed, and then from that I can prepare the matrix. So, from I j k I can from r theta phi this is the relationship with I j k to r theta phi, but I can also do the vice versa, because this is a orthogonal transformation. Last day we mentioned that if we are having a matrix for orthogonal transformation, they are following certain rule, so that if M is my matrix that is making this transformation, so it is following these things. M transpose is equal to unity. So, that means this is because this is orthogonal transformation. So, I can if I so you just make a transpose and you will going to get. So, I am not doing that. So, if you want to get that r theta phi, you will just you need to put the M transpose here, and you will get I j k this side. This is how one can extract the other information from r theta phi unit vector, how get I. Okay, in the similar way, let us quickly find out how that vector will going to transfer. So, now transformation of a vector. So, a vector, a given vector can be written in terms of the Cartesian coordinate system like axi plus ayj plus azk. But the same vector in polar coordinate, spherical polar coordinate, I can write it as ar plus a theta, theta unit vector, plus a phi, phi unit vector. Okay. And the process is similar. So, that is why I am not going to do the detailed calculation. So, the next thing what you need to do, because you now you know the relationship between a and r, j and how you know this, how these things are transformed, right. So, that information I am going to use here, and then let me just write. So, this things is a x in terms of in place of I just simply write the when I is decomposed in r theta phi. So, that matrix is there. So, I can use this matrix and I am going to get this sin theta cos phi r unit vector plus cos theta cos phi theta unit vector minus sin phi phi unit vector. That is one term. Then you should do the next one, and finally you will have the last one. Now, this entire thing again you can decompose like a multiplied. So, okay. So, these things are equivalent to a r r unit vector. So, you can gather all the r unit vector plus a theta unit vector plus a phi unit vector. You gather all these things inside ar, a theta and a phi, and after doing that you will simply find that I am just writing the final expression, which is same actually. After doing all this exercise, you can write simply the relation a r, a theta, a phi is equal to cos phi sin theta, sin theta sin phi, and then cos theta. Here you have cos theta cos phi and minus of sin phi, and then cos theta sin phi here minus of sin theta, and you have cos phi and 0. This matrix you will get the same matrix actually, and this side you should write Ax, Ay, Az. This is your M matrix. So, you can also have the M transpose will be 1. Using that you can also have the other relationship which is same. Okay, I believe you can do that. Now, quickly I go to the next topic that I am going to just start: line element and volume element and surface element. So, the next topic is how to calculate the line element, volume element. So, length, area and volume element in different coordinate system. So, let us start with Cartesian coordinate system first. In Cartesian system, these things are very straightforward. So, I am having a coordinate system, Cartesian coordinate system, x, y and z, and any length here given. Suppose this is a length element, and this length in terms of vector simply given as delta x I plus delta y j plus dz k, not delta but dz. This is the vector we are having. This is simply the differential. This is called the differential displacement. Differential displacement. Well, what is the surface element then? Length element we understand, surface element. This is again the coordinate system. X, y, z, and you can have the surface like this, right? Let me draw the surface. So, one surface you can have this, if I consider the box. Another surface you can have this, and another surface you can have this. This surface, which is where this is my I direction, this surface, this is my j direction, and this surface, this is my k direction. So this length is along this dy and along this dz. This is along this is dx, and this along this is dz. For this we have dx here and dy here. These are the vector quantities, mind it. So my surface element ds is like dy dz I, it can be dx dy k or dx dz say j. These are the differential surface. What about the volume element? Again, volume element is very simple. This will be, volume element is a scalar quantity, so it should not bother much about the direction, where the surface, the direction is important. So if I have a box here simply like this, a volume element I can define. So this is this along this direction, this is dx, along this direction this is dy, and along this direction this is dz. So my volume element simply dv is equal to dx dy dz, as simple as that. So this is called a differential volume element. Well, it looks quite simple and very straightforward for Cartesian coordinate system to find the line element, surface element and volume element. But in the next class we find that it is not that straightforward when you are going to other coordinate system like spherical polar coordinate system or cylindrical coordinate system. It is not straightforward. So in the next class we will discuss how to define these volume element, surface element or line element in those coordinate system. With that note, I would like to conclude here. Thank you for your attention.